the last lecture, we have studied about how to calculate the derivative for the vector functions. So now here let us see some properties of the derivatives. If we assume that this f, g and h, they are three vectors which are differentiable vector functions. So that means we can take their derivatives. So, and this phi represents some scalar function which is also differentiable. So in that case we have several properties. First property is that whenever you take the derivative of the sum of two functions, that is equal to the sum of their individual derivatives. Now this is the proof for this one is very simple. So let me first discuss all the properties with you quickly. The second property is whenever you have some scalar function, scalar point function phi, and some vector f, right, and you take their multiplication and then you are performing the derivative. So in that case this is equal to the scalar field as such, the derivative of this vector function plus the derivative for the scalar field, and then this vector as such. And similarly, so you might be thinking that these properties are very similar to the derivatives which you are studying in order to calculate it for scalar functions. So these are also same for whenever you have vector functions. Now this vector f dot vector g, this represents this vector f dot vector g, this represents the dot product. And how do you define this dot product? It is defined as the magnitude of vector f, the magnitude of vector g into the cos of angle between these two vectors, and this is a scalar quantity, right? So if you take the derivative for this f dot g vector, so this is going to be equal to the derivative of first vector dot product with second vector plus the first vector as such and dot product with the derivative of second vector. The fourth property here is about cross product. Now what is cross product between two vectors f and g? So this is defined like this. This is equal to the magnitude of first vector f vector, the magnitude of second vector g vector into sine of the angle between them, and because this is a vector quantity, so that means it will also have some direction which I am defining by n cap, where what is this n? This gives the direction which is perpendicular to the direction of this vector f and to that of vector g. So in this case, if you take the derivative for this cross product of two vectors, so this would be equal to the derivative for this first function cross product with the second vector, right, and then plus the first vector cross product with the derivative for this second vector. So this is your fourth property. Fifth property is about taking the cross product for three vectors. So suppose you have three vectors f, g and h. If you take the cross product of g and h first and then take its cross product with f, in that case the derivative of this particular quantity is equal to taking the derivative for this one, keeping them these two as such. So it would be derivative of first vector cross product with the second vector cross product with third vector, right, plus the first vector as such cross product with the derivative of the second vector. So that would be dg by dt cross with third vector as such plus first vector as such, second vector as such, and then the derivative for this third vector, right? And moreover, we also have the sixth property concerning about the scalar triple product. Now what is scalar triple product? We denote this by square brackets of three vectors, first vector, comma second vector, comma third vector, and it is defined as the dot product of first with the cross product of remaining two, right? So this is the definition for scalar triple product. And if you take the scalar triple product and then you take its derivative, in that case this becomes equal to the scalar triple product of the derivative of first vector with the second and third vector as such plus the scalar triple product of first and third vector as such, but taking the derivative for this second vector plus the scalar triple product of the vectors f and g as such, first two as such, and then you have this derivative of third vector with respect to t. So these are some of the properties. So let us quickly have a look at all the proofs for all this. So for proving all these properties, we'll mainly go by the definition for derivative. So what is the definition? Suppose you wanted to calculate the derivative of some vector f. So it is defined by limit delta t going to 0, the vector f defined at the point t plus delta t minus the vector f divided by delta t. So this was the definition for calculating the derivative for some vector. We'll use the same definition here. So it is going to be equal to, if you take the left hand side, so we can apply the definition for derivative. So here by definition, because our function is f plus g, so this is going to be change in f plus the change in g, so this is this first quantity, minus the given function as such, divided by delta t. So now we can do some calculations here. So you see, when you open up this term would cancel with this term, and this will cancel with this term. So finally you will be left with delta f plus delta g vector divided by delta t vector. So you could separate out these terms, and then you can take the limits individually, so that this quantity, it becomes the derivative for the vector f, and the second quantity becomes the derivative for the vector g. And this is what we were required to prove here. Okay, moving on to the proof for second property. We wanted to calculate the derivative of the product of scalar point function and the vector f. So in that case, we have considered the left hand side, and we have applied the definition for this derivative. By definition, what we have to do, we have to take its value at the point t plus delta t. So that means we'll take change in this delta. So change in this phi, sorry. So it will be represented by phi plus delta phi, and change in f would be represented by f plus delta f minus the original function as such. So this is using the definition, divided by delta t. So now what we have to do, we have to simplify this expression. Now for simplification, what we will do, we will multiply it simply as we do in other calculations. So we'll multiply this phi with f this vector f. So this would be going to be phi vector f plus then multiplication of phi with this second term, phi delta f vector, plus the multiplication of this term with second term with this first term over here, and then this, right, minus phi vector f as such. So now this term and this term cancels out, so you are left with all these terms. So you just have to divide them, all of these terms, by delta t. So you will get these expressions, and then you will take the limits individually. When you take the limit delta t approaching 0, in that case the first quantity here becomes equal to del f by del t, the second quantity becomes equal to d phi by dt, right, and here the third quantity becomes equal to d phi by dt. But moreover, whenever you take delta t going to 0, in that case your delta f will tend to 0. So this quantity becomes 0 vector. And whenever you multiply some quantity by the 0 vector, that is 0 itself. So this is what you obtain, and this is what we were required to prove for this particular property. Moving on to the next property, property number 3. Here we wanted to show it for the dot product. For the dot product, we again took the left hand side, apply the definition. So we'll take the change in f dot with change in g minus the function as such. Then we'll apply the dot product here. So applying the dot product using the properties of dot product, that simply becomes the dot product of vector f and g plus the dot product of vector f and delta g, the dot product of vector delta g and g, and then the dot product of vector delta f and delta g minus this function as such, right. So this function cancels with this one, right, this dot product, which would eventually be a scalar, right. So this cancels with this one, so you're left with all these terms. So thereafter you divide by delta t, so you have this, and then you take the separate limits, so you have this, and then whenever you tend your delta t to 0, in that case the quantity delta g is also tending to 0, so we have 0 here. So we are only left with this first two terms, so we have this as the right hand side. For the property fourth, here we have to show for cross product. So again we'll take the left hand side and we'll apply the definition. So we'll take the change in f cross with change in g and minus the original function, right? So here we will perform the multiplication applying this cross operator. So it would be vector f cross with vector g plus vector f cross with delta g plus delta f vector cross with vector g, and then plus the cross of delta f vector and delta g vector. Now this and this cancels out. Similarly, we have this quantity. We can separate out the terms and we can take the limits. After taking the limits, you have this as the 0 quantity, and then this becomes equal to right hand side. For the next property, where we are to show this for the triple for three vectors, so in that case we can apply this fourth property, which give you this result, d by dt of vector f cross with vector g. This is equal to this particular quantity, so we can apply this firstly by taking this function and then by taking this particular function. So in this case, when you apply this property here, you will, what do you obtain? You took this term, so you'll obtain the derivative for this first term cross with the remaining as such, right? So this is your first, this is your second vector, because cross product give you another vector, so this would be another vector, okay? And plus we have first vector as such cross with the derivative for second vector, right? So this is applying the property 4. Now we can again use the property 4 on this particular term. So when you apply this on this term, so you will have this to be the derivative for first vector cross with h vector plus g vector as such, it's cross with the derivative for h vector, right? So you can open up this brackets, rearrange the terms a little, so you will have this as the final result, right? So you saw here we do not have to apply the definition exact in order to prove this, because we can use the previous property here. Moreover, there is no such result, there is no result relating to the derivative for the vector f dot with vector g dot with vector h. Why? This is not available, because in order to take the dot product of vectors, this quantity g vector and dot with h vector, this would result into a number or a scalar, right? And in order to perform the dot product, both of these, they should be vectors, right? So this is not defined. And lastly, let us prove this sixth property. For proving this property, we'll take this left hand side, apply the definition for scalar triple product, so this becomes equal to this. Now g cross h is a vector, so you can take the dot product of f with the dot product of g cross h, right? So now in order to solve this, we'll apply the property number 3 for the dot product. So in that case, first vector would be as such, we take the derivative for second plus the derivative of first vector dot with the second vector as such, g cross h. Now this term will not do any calculation on this particular term. However, on the first term we can perform this calculations. So we can go and solve for this particular part. So using the property 4, this becomes equal to this, right? So we can simplify the terms, open up the brackets. So you have all these terms. So now this you can write this term to be this one, similarly this term to be this, and this term to be this, using the definition for scalar triple product. So this is the proof for this sixth property. So I hope you are clear with all these properties and how do you obtain all these properties.